हेलो शिवराम। शिवराम। हेलो। हेलो शिवराम।
हेलो
क्लास ହେଇନି କି?
ସାର୍ ଷ୍ଟାର୍ଟ କରୁନାହାନ୍ତି।
ହଁ ମୁଁ ଜଏନ୍ କରିଥିଲି ମଝିରେ କଟ୍ ହେଇଗଲି ତ। ସାର୍ କରିବେ କି ନାହିଁ କେଜାଣି? ହଉ ଦେଖିବା ୱେଟ୍ କରିବା।
ଲେଖିଛନ୍ତି ଷ୍ଟାର୍ଟ ସୁନ୍ ବୋଲି, ସାର୍ ବି ଜଏନ୍ କଲେ।
କଣ କହୁଛ?
ସାର୍ ଜଏନ୍ କଲେ ପୁଣି ଲେଫ୍ଟ ହେଇଯାଇଛନ୍ତି। ଆଜି କ୍ଲାସ୍ ହବନି ପରା ମ୍ୟାଡ଼ାମ୍। नमस्कार.
So earlier we have discussed slow neutron and fast neutron. So moderator is being used to slow down the neutron and make controlled fission reaction. So now the basic question that may be arised in your mind, that how to slow down neutron. So neutron can be slowed down by elastic scattering, and you can have the slowing down spectrum of the same, and the neutron can also be slowed down by inelastic scattering. That we will discuss in this class. So you can see for scattering, elastic scattering reaction, let us have the following assumptions. The kinetic energy of a neutron is less than 10 mega electron volt in a nuclear reactor. This is very low compared to the rest mass energy of the neutron, which is around 939.5 mega electron volt. And relativistic effect will not be relevant at this level. Then neutron-neutron interaction we have to ignore. So let us assume that neutron-neutron interaction is ignored. Why we ignore this? As ignoring the neutron-neutron interaction, the number density of neutrons is considerably less than the number density of nuclei. And the neutrons move along straightliness between collisions. We assume this. Then we assume that the effect of neutron-nucleus collision are not a function of initial direction of neutron, because the material are isotropic in nature. Isotropic, directional in one direction. The nuclei are always in thermal equilibrium and their velocity distribution is given by Maxwell-Boltzmann law. So assume that nuclei is in thermal equilibrium, and when nuclei is in thermal equilibrium, the velocity distribution of the constituent particles will obey Maxwell-Boltzmann law. Then we shall discuss inelastic collision, and for inelastic collision, both linear momentum and kinetic energy of the system we assume to be conserved. We assume to be conserved. And this approximation may break down in elastic reactions, which we will discuss today. The neutron nucleus collision is isotropic in center of mass system or CM system. It means that the emission angles of secondary particles are equally probable. This approximation fails when energies of incident neutrons are greater than 1 megaelectron volt. The angular distribution of emerging neutrons is isotropic in the center of mass system at energies up to 5 kiloelectron volt for heavy nuclide and up to 50 to 100 kiloelectron volt for light element. The forward anisotropy increases with increasing neutron energy and decreasing mass of the target nuclei. The nuclei move freely between collisions. So the nuclides are free from any atomic or molecular binding forces. However, when energy of the incident neutron is less than 4 electron volt, metallic binding forces influence it. If the nuclide is used as moderator for deuterium, for heavy water, graphite, etc., or salted water, and by assuming these things, we shall derive the collision kinematics of a neutron, when collide with the nucleus. So here is the laboratory and center of mass coordinates. So it is shown in the picture. I think it is visible. So your OL will be MRL plus capital MRL by small m plus capital M, where small m is the mass of the neutron, capital M is the mass of the nucleus. RL, small rl is the position vector of neutron, and capital RL is the position vector of the nucleus. So your velocity will be Vc, will be VL minus V0, and your V0 can be written as MVL plus capital M VL by M plus M, and your VL will be 0. VL will be 0, so Vc is equal to minus small V0. So by putting that in the formula, you will have this picture. The neutron in center of mass coordinate, it will approach toward the target nuclei, and initially the mass of the neutron will be m, small m, and velocity will be small vl, and after the collision, the velocity of the compound nuclei, before the collision, the velocity of the target nucleus will be vl. So after the collision, it will directed with an angle delta L from the center of mass coordinates, and your target nucleus will in some other way. So before collision, you can see that target nucleus in the left hand side, your neutron and target nucleus, and after collision in the right hand side. So kinetic energy of a neutron after collision in the laboratory system can be pictorially represented in vectorially in the picture as shown in the screen. So using the law of cosines, you can have VL dash square is equal to Vc square plus V0 square plus 2 Vc V0 cos theta c, where theta c is the angle between VL dash and Vc dash or Vc. Then you can solve this equation and you will get EL dash by EL is equal to 1 plus alpha by 2 plus 1 minus alpha by 2 cosine of theta c. So when theta c is 180 degree, your EL dash will be minimum, and the equation will be modified accordingly. For hydrogen, alpha is equal to 0, EL dash is equal to 0. And it is possible for a neutron to lose all its energy if it collides with a hydrogen nuclei. Hence we use heavy water, D2O. Maximum energy transfer during elastic collision for hydrogen or any other nuclei will be 1 minus alpha EL. And if theta c is equal to 0, then the neutron would lose no energy. Such a reaction is known as Glensin collision. Then scattering angle of a nucleon in a laboratory system can be evaluated by using the formula cot theta L is equal to capital D by B, where the expression for D and B are shown in the screen. From this you can have your cos theta L, which is A cos theta C plus 1 divided by root over of A square plus 2A cos theta C plus 1. And for hydrogen, where A is equal to 1, your cos theta L is equal to root over of 1 plus cos theta C by 2. So when theta C is equal to 0, theta L is equal to 0. When theta C is equal to pi, theta L is equal to pi by 2 by putting this in the equation. So theta C goes from 0 to pi and theta L goes from 0 to pi by 2. And for heavy mass elements such as uranium, your A will be very, very greater than 1. The mass number is very, very greater than 1. Either 235 or 238 or so A will be very, very large. So your cos theta L will be A cos theta C by root over of A square, which is nearly equal to cos theta C. So your center of mass and lab frames coincides with each other for heavy nuclei like uranium, thorium, etc. So the average cosine of scattering angle in a lab system, mu L, can be calculated. And for that, you take the expression P theta C d theta C is equal to sin theta C d theta C by 2, which is nothing but sin theta C by 2. And the scattering into a solid angle element d omega is equal to dA by R square as shown in the screen. So from that, you can have your mu L is equal to 2 by 3A, where A is the atomic mass of the nuclei. So for hydrogen, A will be 1. So it is 2 by 3. And this relation will applies to materials other than hydrogen, uranium, thorium, and others. Then after in a scattering, neutron scattering process, scattering probability distribution will be evaluated, and it will be shown as the graph as shown in the screen. In the x-axis you have your E, and in the y-axis P. So isotropic scattering, forward scattering, backward scattering are shown in the screen. Then an average energy loss in such type of collision will be del E bar is equal to EI minus EF bar, which is nothing but 1 minus alpha EI divided by 2. And neutrons suffering scattering collision in hydrogen will lose on the average half of their original energy in each collision. However, with uranium-238 nucleus, they will lose on the average less than 1% of their original energy. From this equation, you can have these conclusions or inferences. Then differential elastic scattering cross section, you can calculate it by using the formula sigma s, which is a function of E, is equal to integration 0 to infinite sigma s E2 E dash d E dash. And differential scattering cross section in lab and center mass coordinate system can be evaluated, and your sigma L, which is a function of theta L, will be sigma in center mass coordinates, which is a function of theta C, multiplied by A square plus 2A cos theta C plus 1 to the power 3 by 2 divided by A square cos theta C plus 1 plus A. Then the second part of the scattering problem, average logarithmic energy decrement. So this can be evaluated, and you have the graph as shown in the screen, mass number versus your Xi. So Xi is independent of energy, E. So the approximate value of Xi can be calculated using the formula 2 by A plus 2 by 3. And for A is smaller than 10, the error associated with the formula is about 1%. So for A smaller than A, this will be very exact. This will give very exact result. So this plot of average logarithmic energy decrement versus A for different nuclei with exact and approximate formulas are shown in dotted line and solid line. And your Xi can be evaluated using the formula 1 plus A minus 1 square by 2A ln A minus 1 by A plus 1. And by simplifying it, you will get 2 by A plus 2 by 3, where sigma is independent of energy. Then relationship between energy and lethargy. So what is a lethargy? If E1 is the lethargy corresponding to energy of neutron before collision, and U2 is the lethargy after collision corresponding to neutron energy E2, then del U can be written as U2 minus U1 is equal to ln U1 by E2, and J is the average lethargy change per collision. So 1 by J gives the average number of collisions per unit lethargy change, and J is independent of energy, and a neutron suffers the same number of collision for the same specified change in lethargy.
Sir, what do you mean by
Then
lethargy?
average value of number.
Excuse me, sir.
Excuse me.
Sir, lethargy means what, sir?
The energy range spanned in neutrons slowing down by elastic collision is very large. Okay. So
Okay, sir.
let me explain. The energy range spanned in neutrons slowing down by elastic collision is very large, as I have told you earlier, and it may range from 10 to the power 7 electron volt to 1 electron volt. And in elastic scattering with a given nuclide, neutrons tends to lose a fixed fraction of their initial energy rather than a fixed value of energy, fixed fraction of the initial energy rather than a fixed value of energy. These considerations suggest that if it would be more convenient to use an independent variable like logarithm of nuclear energy E, you can have a dimensionless quantity U. And this dimensionless quantity U is called mutant lethargy. And you can define U by using the formula ln E0 by E, where E0 is maximum energy that neutrons have, and E is the energy of the neutron. Okay. So U is ln E0 by E. So when you know the E0 is maximum energy of that neutron, then you can calculate U. So I have told you earlier that it is not the it do not represent an absolute value. It do not represent an absolute value, rather a fraction, a fixed fraction. Okay.
Yes, sir, clear.
Fixed value of energy cannot be represented in this case. So we use a fixed fraction of their energy, and fixed fraction can be evaluated from ln E0 by E, where E is the total, E0 is the total energy, and E is the energy of the neutron. So E0 by E will be the fraction of energy, and the logarithm of this will give you a dimensionless quantity U, which is called lethargy. Are you getting it?
Okay, sir, clear.
And it is shown in the screen.
Yes,
Mass
sir.
number versus J, where your U is embedded in this J expression. Then relationship between energy and lethargy. So U and E0. So you can see that E0 decays, E0 changes, it is somehow a logarithmic curve, and in each point you have a fraction of energy. You can have this. So this in x-axis, in y-axis you have your lethargy, and in x-axis you have lethargy, and in y-axis the energy of the neutron. So this represents the x coordinate. This represents a particular lethargy. This another. This so a partial E0 by E in a logarithmic term. So E can be represented as E0 e to the power minus E. Okay. And now see, slowing down parameter of typical moderator. So you can use due to heavy water, your helium, beryllium, carbon, oxygen, all these things as a moderator. And for different moderator, maybe it hydrogen, deuterium, water, heavy water, helium, beryllium, carbon, oxygen, uranium-238, your A, alpha, Xi, rho, N star, Xi, sigma S, Xi, sigma S by sigma A. All these values are shown in the screen in a tabular form. So here are some worked out examples. So here is a problem. So that lethargy आप बोल रहे थे. So let us have so that the large mass number of J is nearly equal to 2 by 1 A plus 2 by 3. So this is derived, this can be derived. So you can see here the solution. And if you have any doubt, then I shall explain. See the formula for xi, 1 plus a minus 1 square by 2a ln a minus 1 by a plus 1. From there, using the identity and simplifying it, you can have the RHS of the expression. Okay. Then we shall discuss the spectrum. Neutron slowing down without absorption. Diagram for analysis of slowing down in a hydrogen-like moderator. The easiest case is to moderation of spectra of neutron in an infinite homogeneous hydrogenous medium containing uniformly distributed sources. To solve the slowing down equation, we assume that no neutron absorption takes place, no space dependence, and source S of neutrons per unit volume per unit time at energy. So P from E0 to E d can be written as d by E0. So by solving it, we will have Fe is equal to S by sigma S, which is a function of E multiplied by E. So the slowing down density Q can be written as Sc by E0 plus E integration E to E0 Fe dash d dash by E dash. So you can write Q is equal to S, capital S. And moderation of neutron in a medium with A greater than 1, except hydrogen. For hydrogen like atom, we have discussed, and for other atoms, other than hydrogen atom, even for deuterium, you have your sigma S phi is equal to integration 0 to E by alpha d dash sigma S from E dash to E phi, which is a function of E dash plus S. By solving it, you will have your F1 E dash is equal to 0 below alpha E0, and F2 will be written as integration E to E by alpha F1, which is a function of E dash d dash by 1 minus alpha E dash, and your for this is for the region alpha square E0 is smaller than E is smaller than alpha E0. So slowing down neutron in a medium can be shown in the transition, so as shown in the screen, and you can have the spectrum. And your Q, which is a function of E, can be written as integration E to E by alpha Fe dash d dash multiplied by E minus alpha E dash divided by 1 minus alpha E dash, and this can be simplified as Q is equal to C 1 plus alpha by 1 minus alpha ln alpha, which is equal to C xi, where xi is the average logarithmic energy decrement for collision, which we have discussed earlier. And the value of Q has to be equal to the source density. So your source density is S for an infinite pure scattering medium, assuming steady state behavior without absorption. So the constant C can be written as S by xi. So here is the flux after n collisions with a monoenergetic neutron source in a purely scattering infinite medium. So your Fe will be S by xi E, and phi can be written as, which is energy dependent flux, which is a function of E, can be written as S by Xi sigma S E. So you can see in a logarithmic scale, the graph will be look like as shown in the screen. So you can see in x-axis you have energy, and in y-axis flux of neutron after n collisions, and it is in energy units. Similarly, energy versus total flux in logarithmic scale as shown in the screen. So first it will be constant, then there is a sharp increase, then rapid decrease, rapid fall. Total flux per unit lethargy with monoenergetic neutron source in a purely scattering infinite medium. The neutrons slowing down with absorption in an infinite medium moderator and resonant observer can be evaluated, and you can see comparison of Xi and the constant lambda for various moderators, hydrogen, deuterium, beryllium, and carbon, Xi and lambda value. And in Wigner approximation, the value of lambda is approximated by Xi in the equation lambda is equal to 1 by Xi 1 minus alpha multiplied by 1 minus alpha omega minus alpha omega square by 2, which gives the result. And the fact that lambda is smaller than Xi means that smaller self-shielding of Gg compared to Wigner approximation. Gg is Grueling-Guezel approximation, where Q, which is a function of E, can be written as integration from E to E by alpha sigma s phi E minus alpha E dash by 1 minus alpha E dash d E dash. The kinematic of inelastic scattering, which we will discuss now, and in this type of scattering, the incident neutron by a target nucleus is quite similar to that of elastic scattering, except that the total kinetic energy is not conserved in the former. The Q value of the reaction has to be taken into account for the conservation of the total energy after the collision. However, conservation of linear momentum holds good. Hence, in deriving the kinetic parameters for inelastic scattering, the notations used for elastic scattering will be used. And you can you know that V0 is VL by A plus 1, which we have discussed in elastic scattering, and Vc is equal to Vc dash, which is A VL by A plus 1. And by solving it, you have your E thermal is equal to A plus 1 by A Q. So its minimum value will be EL, or E threshold will be A plus 1 by A modulus of Q. So this threshold energy is dependent upon A, the value of atomic mass, and Q. And for an inelastic scattering event to occur, the neutron are required to have a laboratory kinetic energy in excess of A plus 1 by A times that of the excited energy level. As A increases, E threshold is almost equal to the Q value numerically. And in the first and second excited levels in some nuclides are shown in the tabular form for carbon, oxygen 16, sodium 23, iron 56, uranium 235, uranium 238, and plutonium 239. Then energy spectrum of inelastic scattering neutrons. So you can see N, which is a fast neutron, will bombarded upon the target nuclei, and a compound nucleus will be formed. Then at an angle, NDS will move away and gamma ray will be emitted. And inelastic scattering terms in energy levels of target and product nuclei is shown in the screen. Here, inelastic scattering group 1, 2, and compound elastic group, and the transition and the emission of gamma rays. So this is the energy, available energy in central of mass system. So you can see discrete energy spectrum for inelastic scattering neutron, energy of scattered neutrons in y-axis, and these are inelastic neutrons and these are elastic neutrons. And T can be written as 3.2 into root over of E by A. And this is continuous energy spectrum of neutrons from inelastic scattering of 10 mega electron volt neutron by uranium 238. So it will E in y-axis and E gas in x-axis. So it will increase, and after that it will decrease. The average energy of an inelastic neutron will be E bar gas is equal to integration 0 to infinite E dash P from E to E dash D E dash, which is nothing but 2 capital T. And for the inelastic scattering of 10 mega electron volt neutron with uranium-238, E dash bar is 1.32 mega electron volt. And the incident neutrons on the average loses 8.68 mega electron volt as a result of single inelastic collision with uranium-238. It is to be noted that average energy loss by elastic scattering will be half 1 minus alpha 10 MeV, which is up to nearly 0.085 mega electron volt. So you can see for elastic scattering, it is less than 0.1 mega electron volt. For inelastic scattering, it will be around 10 mega electron volt. And differential inelastic scattering cross section can be calculated, and inelastic from E to E dash will be sigma inelastic E multiplied by K inelastic is equal to E to E dash. And you can solve it. And you can have the relationship between the energy and the cosine of the scattering angle in the lab and center of mass system. So EL dash will be C dash plus EL plus 2 mu C, A plus 1 root over of EL EC dash divided by A plus 1 square. And your mu L can be written as mu C root over of EC dash by EL plus 1 by A plus 1 root over of EL by EL dash. The angular distribution of inelastically scattered neutrons, inelastically scattered neutrons N, are quite simple over most of the energy range of interest in reactor theory. Up to around 10 mega electron volt, these neutrons are emitted isotropically, or nearly so, in the central mass system. Above 10 mega electron volt, the angular distribution tends to become forward peaks and exhibits a diffraction pattern similar to that found in elastic scattering at these energies. The forward peaked distribution is due to neutrons undergoing direct interaction type of inelastic scattering. Since there are comparably few neutrons with such a large energy in nuclear reactors, it is usually adequate in reactor theory to assume that inelastic scattering is always isotropic in the central mass system. However, the effects of inelastic scattering anisotropy are accounted in the present reactor calculation with the help of multi-group cross-section. Okay. So we shall discuss block 3 in the next class, and you can have this is for inelastic scattering. If a 10 mega electron volt neutron collides with uranium-238 nuclide, compare the average energy loss of the neutron if they undergo inelastic scattering and elastic scattering. So you can have this. The average energy of inelastic scattered neutron is related to nuclear temperature, and the nuclear temperature T is given by 3.2 root over E by A. So E is here 10 mega electron volt, A is mass number 238. So it will be 0.656 mega electron volt. The average energy of inelastic scattering is therefore 1.312 mega electron volt. It means that the incident neutron loses an average of 8.68 mega electron volt as a result of single collision with uranium-238 nucleus. On the other hand, for elastic collision, assuming isotropic scattering in central mass system, the average energy loss can be calculated using the formula half 1 minus alpha En, where alpha is equal to 0.9833 for uranium-238, and the value of your T will be 0.0835 mega electron volt. Similarly, so that the width of energy distribution of inelastically scattered neutron from heavy nuclide in the lab system is very narrow. You can calculate it, and you can see that your for A is very greater than 1, your E max minus E min by EL is equal to very smaller, equal to 4 by A, which is very narrow. Okay, so in the next class we shall discuss block 3. So we have covered block 1 and 2. Then in the next class we shall discuss block 3. Okay, thank you.
Hello, sir. Hello.
Yes,
हेलो सर मटेरियल साइंस आमे नेक्स्ट पढ़िबा कि ये रिएक्टर फिजिक्स सरला परे
हाँ यहाँ पर मटेरियल साइंस आई थिंक
ओके ओके थैंक यू सर
ଆର ବହିଟା ଆମେ ପାଇନୁ ସାର୍ କଣ କର
Hello. Hello, Sam Siddha is here. Hello.
Yeah. Hello,
Hello, ma'am. Where are you from?
I'm from Sundargarh.
You are from Sundargarh.
Yes.
Am I right?
So has like
Hello.
hello.
ଆପଣ ସୁନ୍ଦରଗଡ଼ର?
ହଁ।
ଆଚ୍ଛା।
सर लेफ्ट ହେଇଗଲେ ତ କ୍ଲାସ୍ ଏଣ୍ଡ ହବ କି?
ସାର୍ ତ କହିଲେ 8ଟା ହେଇନଥିଲା ଆଉ ସାର୍ କହିଲେ କି ଏଣ୍ଡ ହେଇଗଲା ବୋଲି।
ହଁ।
ଆପଣଙ୍କ ଷ୍ଟଡି ସେଣ୍ଟର ବିଜେପି?
ହଁ ଷ୍ଟଡି ସେଣ୍ଟର ଟା ବିଜେପି।
ଏକ୍ଜାମ ସେଣ୍ଟର କୋଉଠି ଅଛି?
ଏଇ ସୁନ୍ଦରଗଡ଼ ଗଭର୍ଣ୍ଣମେଣ୍ଟ କଲେଜ।
ଆପଣଙ୍କ କୋଉ ବ୍ୟାଚ୍? ଜାନୁଆରୀ ନା କଣ? 24 ନା ଆଉ କୋଉ
ଆମର
ବ୍ୟାଚ୍?
ନାଇଁ ଜୁଲାଇ 2023।
23 ବ୍ୟାଚ୍।
ହଁ ଆପଣଙ୍କର?
ମୋର 24।
ଆଚ୍ଛା।
ସମ୍ବଲପୁରୀ ଆସୁଛି?
ହଁ
ଆଁ?
କେନର୍ଥ
Actually ମୋର ମାଙ୍କର ଘର ସେପଟେ ବହୁତ ସୋନପୁର ପାଖ।
ଓହୋ ଆଚ୍ଛା।
ସୁନ୍ଦରଗଡ଼ରେ ବି ସମ୍ବଲପୁର ନା। ଆଉ ଗୋଟେ କିଏ
ସୁନ୍ଦରଗଡ଼
ପିଲାଟେ ଆମ ସାଙ୍ଗେ ପଢୁଛି ସୁନ୍ଦରଗଡ଼ ଗୋଟେ ଅଛି ଆମ ବ୍ୟାଚ୍।
ଆଶିଷ ପଟେଲ।
ନାଇଁ। ମନେ ନାହିଁ ପଡିଲା। ମନେ ନାହିଁ ପଡିବା ସେମିତି ଏକ୍ଜାମ ରେ ଦେଖା ହେଇଥିଲା।
ଓହୋ।
ଆପଣଙ୍କ BSc ସୁନ୍ଦରଗଡ଼ରେ ଥିବ?
ହଁ ଗଭର୍ଣ୍ଣମେଣ୍ଟ କଲେଜ।
ମାନେ PG ଟା ବି ରେଗୁଲାର କରିବା କଥା।
ହଁ ପିଜି ଟା
ମ୍ୟାରେଡ୍ ନା ଅନମ୍ୟାରେଡ୍? ବ୍ୟାଚଲର?
ନାଇଁ ଅନମ୍ୟାରେଡ୍ ହଁ।
ସେଥିଲାଗି।
ଜବ୍ ଲାଗି ଇଏ କଲି ତ ଡିଷ୍ଟାନ୍ସ ରେ।
ଟିଚିଂ କେନ୍ ଫିଲ୍ଡରେ ଅଛନ୍ତି?
ଟିଚିଂ ତ ମାନେ ଟ୍ୟୁସନ ପଢଉଛି +2 ଫିଜିକ୍ସ।
ଆଚ୍ଛା। ପଢଉଛନ୍ତି ବୋଲି ଟଚ୍ ଅଛି।
ହଁ।
ସାର୍ ତ ଖାଲି ଗାଇ ନଉଛନ୍ତି।
ହଁ ପରା।
କହିଲେ ବି ଶୁଣୁନାହାନ୍ତି।
ମ୍ୟାଥମେଟିକାଲ ଇକ୍ୱେସନ ବି ପୁରା
ଓ
ଗାଇ ଦଉଛନ୍ତି।
କାଁ କହିବ ଏଇନେ କହିନେ ହବ।
ହୁଁ।
ମାନେ ଆଉ ଜଣେ ସେ ସାର୍ ଙ୍କ ଟା ସରୋଜ ସାର୍ ଙ୍କ ଟା କରିଥିଲ ବୋଧେ ନାଇଁ କି?
ହଁ ସେ ପାତ୍ର ସାର୍ କରିଥିଲେ ହଁ।
ହଁ ସରୋଜ ସାର୍ ଙ୍କ ପାତ୍ର ସାର୍ ଭଲ ଯାହା ହେଲେ ବି ସେ ଏକ୍ସପ୍ଲେନ କରିକି କରନ୍ତି।
ହଁ ସେ ଦୁର୍ଗା ସାର୍ ବି କରୁଥିଲେ।
ତାର ଆଗରୁ ଆଉ ଗୋଟେ ମ୍ୟାଡାମ ଥିଲେ ସୁନନ୍ଦା ମ୍ୟାଡାମ।
ଓହୋ।
ଆପଣ ବୋଧେ ଜଏନ୍ ନାଇଁ କରିଲେ।
ନାଇଁ ତାଙ୍କର ଫେର୍ କ୍ଲାସ୍ ଅଛି ବୋଧେ ଏଇ 16 ନମ୍ବର ଗ୍ରୁପରେ
ନାନୋ
ନାଇଁ
ସାଇନ୍ସ
27
ଅଛି
ନମ୍ବର ଗ୍ରୁପରେ।
ଲାଷ୍ଟ
ହଁ ମୁଁ
ନାନୋ
ଏଇଟା ଦେଇ
ସାଇନ୍ସ
ସାରିଲିଣି ନା ତ।
ଦେଲେ ନା?
ହଁ।
ଆପଣ ଏକ୍ଜାମ ଦେଇ ସାରିଛନ୍ତି ନା ଏବେ ଜୁଲାଇରେ ହେଲା?
ହଁ ଏଥର ଦେଇ ସାରିଲିଣି ଜୁନରେ।
ଭଲ ହେଇଛି ରେଜଲ୍ଟ?
ହଁ 33 ଆସିଛି ଗୋଟେ ୟୁନିଟରେ ଲେଖା ହେଇଥାଏ ନା ବହିର।
33?
ହଁ ମାନେ
ତାହେଲେ
4ଟା ୟୁନିଟ
66 ହେଇଥିବ।
ହଁ 4ଟା ବ୍ଲକ ଭିତରୁ 3ଟା ନା ଲେଖା ହେଇଥିଲା। ବୋଲେ 3ଟା ବ୍ଲକ ଯାହା ଇଏ କରିକିନା ଆଗରୁ ବି ଜାଣିଥିଲି ଟିକେ।
ଷ୍ଟଡି
+3 ବେଳେ
ମେଟେରିଆଲ ପାଇଛ ନା
ପଢିଥିଲି।
କଣ?
ହଁ ଷ୍ଟଡି ମେଟେରିଆଲ 3ଟା ର ଥିଲା ତ ଭିତରୁ ଏକ୍ଜାମ ଦେଇଦେଲି। ଆଉ ବାକି ଯେନ୍ ଗୋଟେ ବ୍ଲକ ଟା ଏଇଟା ଅପଡେଟ ହେଲା କି ନାଇଁ କିଏ ଜାନେ।
ବେଶୀ ଟଚ୍ ଥିବ ପଢଉଛନ୍ତି।
ହଁ +3 ରେ ବି ଏଇଟା ପଢେଇଥିଲେ ତ ଟିଚର।
ନାନା ସେ
ହଁ।
ଆପଣ ସବୁ କ୍ଲିୟର
ଏଇଟା
ହେଇଛି?
ଇଲେକ୍ଟିଭ ଥିଲା। ହଁ ସବୁ କ୍ଲିୟର ଅଛି ଖାଲି 5ଟା ପେପର ନେଇଦେଇ ସେଟା ଅଛି।
କେନ୍ଟା ନେଲେ?
13, 14, 16, 25, 26।
13, 14, 15, 26।
ହଁ।
ଏବେ ଟିଚିଂ କରୁଛନ୍ତି ନା ନାଇଁ? କାହିଁ ନାଇଁ
vacancy
ଦେଲେ ଯେ
ତ
ଫର୍ମ ଫିଲପ୍ ନାଇଁ
ନାହିଁ
କଲେ?
ଅଛି। ନାଇଁ ଲାଷ୍ଟ ଥର ସବୁ ପଢି ନି ପାରିଲେ ନା ତ ଗ୍ରେଡ କମ ହେବା ଦେଖି ନେଲେ।
ବୋଲେ ନାଇଁ ଲେଖିଲେ ମାର୍କ ଦବାନି।
ହଁ ବୋଲେ ଲେଖିଲେ ବି ମାର୍କ
କିଏ
ଦେବାନି।
ପିଲାମାନେ ତ 0, 2, 3, 6 କର।
ଏଥିରେ 12 ନମ୍ବର ପେପରରେ ଆସିଥିଲା 25 ମାର୍କ 50 ମାର୍କ। ଗୋଟେ ଭଲ ଦେଖିଥିଲି ହେଲେ ବି 25 ଆସିଲା ଆଉ।
ନାଇଁ ଦବା ଟିକେ ଲେଖିଲା ବି ନାଇଁ ଦବା।
ରିଭାଲୁଏସନ ଥିଲେ ହିଁ ପକାବାର ବାଇଚାନ୍ସ କମିଯିବ ଗଲେ ଅସୁବିଧା।
ଅଲଗା ପିଲାମାନେ ତ କେମିତି ରେଜଲ୍ଟ ହଉଛି ତମ ସେମିତି ଏକା?
ଅଲଗା ପିଲା ତ ହଁ ଅଛନ୍ତି ତ।
ଫିଜିକ୍ସ କେମିଷ୍ଟ୍ରି ଆପଣ ନେଇଥିଲେ ନା BSc ରେ?
ହଁ PCM।
ଆପଣ BSc ପାସ୍ ଆଉଟ୍ ଏବେ ହେଇଥିବ ବୋଧେ?
ହଁ
ଜୟଲଲିତ।
କଣ କଣ?
BSc କେବେ ପାସ୍ ଆଉଟ୍ ହେଇଥିଲେ ଏବେ ହେଇଥିବେ କେବେ ଗୋଟେ?
ନାଇଁ ନାଇଁ 2020 ରେ।
20
ହଁ
20
ତାପରେ
ଏବେ ତ
B.Ed କଲି। ହଁ
B.Ed ସରିଛି?
ହଁ B.Ed ସରିଲା MSc
ଗଭର୍ଣ୍ଣମେଣ୍ଟ B.Ed?
ନାଇଁ କୁରୁକ୍ଷେତ୍ର।
ଗଭର୍ଣ୍ଣମେଣ୍ଟ B.Ed ନା ଆଉ କେନ୍ B.Ed କରିଛ?
ନାଇଁ କୁରୁକ୍ଷେତ୍ର ୟୁନିଭର୍ସିଟି।
କୁରୁକ୍ଷେତ୍ର?
ହଁ
ଆଚ୍ଛା ମୋର ବି ଆନ୍ଧ୍ରାରେ ମୁଁ କରିଛି।
ଓହୋ ଆଚ୍ଛା ଆଚ୍ଛା। ଆପଣ କେନ୍ ଗ୍ରୁପରେ ଅଛନ୍ତି ଜି ମୁଁ ଟିକେ ରଖୁଛି ଜି।
ହଁ ହଁ ବାଏ ବାଏ।
नहीं नहीं क्लास खत्म हो गया क्लास खत्म हो गया ମୁଁ ଟିକେ ରଖୁଛି ମ୍ୟାଡ଼ାମ।
ବାଏ ବାଏ ବାଏ।
ହଁ।